Alright, make sure you have your wind worksheet out, and as you watch this video, pause when you need to either make corrections or improve the notes you took. The first thing you were asked to do is to watch some of this time-lapse video that shows 14 years of weather, obviously sped up. And hopefully what you noticed is, in general, these systems tend to move from the west towards the east, and sometimes they kind of swirl around as they go. From your notes on wind, we learned that areas that have clouds tend to be low pressure areas because that's where air is rising and forming clouds. Again, in general, our weather moves to the east, which means in Minnesota, our weather really comes from North and South Dakota. So if you want a quick weather forecast, just see what's going on in the Dakotas. Alright, the next part of your sheet, you took some notes on types of winds, and I'm really going to focus on the westerlies, the jet stream, and the local winds. So look at your notes on the westerlies. And the first thing to understand is that our planet has global wind belts. And this is simply because our planet is unevenly heated. The equator is warmer than any other region. And so we have convection happening, where warm air is rising and cool air is sinking. And when we look at the whole planet, it's a little more complicated. We have these huge convection zones. Now these winds are in the upper atmosphere, up in the stratosphere, or the upper troposphere. So these are not winds that you feel down here at the surface. They affect weather, but these aren't the winds that blow your hair around or that you fly a kite in. They're higher up. And to make things more complicated, this model only works if our planet isn't spinning. But since our planet is spinning, there's something called the Coriolis effect that is going to change the direction of these winds. I'm going to have you watch this movie and see if this helps you understand how a spinning Earth affects the directions that winds travel.
An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement. In the southern hemisphere, the deflection is to the left.
Okay, so the idea here, if that video was confusing, the big idea is that when objects try to move across a spinning surface, they can't go straight. They get deflected or bent to the left in the southern hemisphere and to the right in the northern hemisphere. So some of you might be thinking, is that why hurricanes spin? And it is why hurricanes spin. Alright, so this model is only correct if the Earth isn't spinning. But since it is, what actually happens is we get these wind belts that move from west to east in this latitude, from east to west in this latitude, and you can just follow the arrows. So since Minnesota is in 45 degrees latitude, we are right up here. So we are in the zone called the westerlies, which means weather gets moved from the west to the east. If we were to live at a different latitude, our weather would move in a different direction. All right. So again, just to recap, our weather comes from the west. So the next section of your notes is about something called the jet stream. Again, the jet stream's way up in the atmosphere at the border between the troposphere and the stratosphere, and it doesn't actually affect the whole planet. It's only in a certain region. There's two jet streams, and I'm going to just talk about one that tends to sit between Canada and the border of the United States, and it moves from day to day. It's kind of like a snake or a belt that goes around the whole planet, and it sometimes shifts north and sometimes shifts south, but it's kind of like a border. If you are north of the jet stream, you're probably sitting in a colder air mass, and if you're south of the jet stream, in a warmer air mass. So let's look at North and South Dakota. In the upper image, they're sitting on the cold side of the jet stream, so their weather was probably colder that day. And then down here, because the jet stream moved, they're now sitting south of the jet stream, so probably in a slightly warmer air mass. And since that changes from day to day, that is one thing that affects our weather. So some quick notes. So it's about 6 to 9 miles above sea level. Again, it does not blow your hair around. It's way up in the atmosphere. It also blows from west to east at speeds of 100 to 300 miles per hour, so it's a very fast-moving wind. And its position changes from day to day, which is why it affects our weather. So something for you to think about. Here's a plane ticket from Seattle and back. So notice my trip to Seattle is 3 hours and 36 minutes, but my trip home is 30 minutes less, 3 hours and 6 minutes. If I look over here, it's not because my distance is different. The distance is exactly the same. So why would the flight time be a half hour different? Again, the distance is the same. So I'm flying to Seattle and then back. And flying home is half hour shorter, half hour less time. The answer, if you haven't figured it out, has to do with the jet stream. When you fly in an airplane, you're up at the upper troposphere. And so if you're flying to the east, the jet stream can actually kind of give you a boost. You can fly with the wind. But when you're flying to the west, you actually have to fly against that wind belt, and that slows you down. Last section is kind of a review. Local wind, that is wind that we feel down here at the surface. It is mostly affected by uneven heating, by rising air, sinking air, things like that. So we talked about that. That should match your notes that we already took. So local winds are winds we feel down here at the surface. They're the winds that you're writing in your notes every day. So your questions. Minneapolis is at about 45 degrees north latitude. We are in the westerlies. And then the last question had to do with the position of the jet stream. This is actually where the jet stream was on March 6, 2014. So we were sitting right in between the colder Canadian air and the warmer southern air here. So I wanted you to make a prediction. What was going on with the jet stream last winter when we had the polar vortex and it was 30 below and 40 below many, many days? So hopefully you made a guess and you wrote in pencil. Here's how it looked. So this gray, here's Canada and the Arctic and the United States. The jet stream came so far south, notice it's down by Texas and Florida. It came so far south that we were actually sitting in Arctic air. The air that should have been up here got pulled way down to Minnesota. So we were actually sitting in an Arctic, a very cold air mass. If you want these notes in your digital notebook, take some pictures and put them in your notebook. And make sure, as always, you ask any questions that you have.